Good evening, everyone. Am I audible to you clearly?
Yes, ma'am.
Okay, is my screen visible?
Yes, ma'am.
All right, so we'll start at 6 o'clock. Let's wait few more minutes so that others can also join. Meanwhile, if you have any queries or anything that you want to ask me, feel free. All right, it's 6 o'clock. Maybe we can begin. So, good evening, everyone. I am Desharda Devi, a PMRF fellow from IIT Gandhinagar. I welcome you all to this live problem solving session on analog circuits course. This session will be held every Tuesday from 6 p.m. to 8 p.m. All the whole session will be recorded, and you can find the link in YouTube. You can directly access my channel through D Sharda Devi. So my channel name is also D Sharda Devi. So the moment you search this on YouTube, you can get through my channel, and all these videos I'll upload them immediately. So by around like 9 o'clock, 9:30 at night, after the session you can start accessing the videos, and also the PDF of this document which I'll be sharing with you, where we'll be solving the problems. This document will also be available to you on a shared drive link, which will be available to you through NPTEL's weekly log list. There you can find the shared drive link where you can file all the PDFs for the corresponding weeks. And yeah, with that, let's quickly dive into today's session. So, in this particular course, what we will go through is basically op-amp based circuits in the beginning. To start with, in the first week, we will have introduction on pole zero concept, ideal op-amp, applications of op-amp, etc. In week two, we will continue with the applications of op-amp like summers, difference amplifiers, integrators, differentiators, etc. In third week, we'll look into the non-idealities in the op-amp, like finite gain, bandwidth, slew rate, saturation, offset voltage, bias current, etc. In fourth week, we'll look into Bode plots, frequency response, Miller's theorem, feedback, and effects of feedback. In fifth week, we'll look into stability, Nyquist plots, phase margin, gain margin, frequency compensation, etc. Sixth week, we'll have filter design, where we will look into Butterworth and other kind of different filters. In seventh week, we'll dive into some electronic devices like diodes and BJT circuits, which are very basic. And in eighth week, we'll conclude with a few more BJT based circuits. So this is how the course has been planned, and this is a 8-week course. And each week we will have a corresponding live problem solving session as well. So to start with, in today's session, before we dive into the problems, let's look a little bit into op amps. Okay. So when we say op amps are the full form of op amp is operational amplifier, and we denote it with this triangular box. Which has one output and two inputs. And this is op amp. So the idea of an op-amp is it's a differential amplifier. Basically, what we mean by differential amplifier is the output of your op-amp is actually gain times the difference between two inputs. Okay, so this is the idea of the op-amp. It amplifies the difference of the inputs. And if we talk about an ideal op-amp, so the ideal op-amp has very high gain. It has very high gain, and if I talk about the voltage transfer characteristics of an ideal op-amp, or let's say, okay, let's say ideal op-amp, and it, if we draw V out versus V in, what we observe is okay, so this op-amp basically works with two bias voltages. plus VDD and minus VDD. So ideally, the input range that it offers is very small. And if we take a practical op-amp, then also the input range is very small. So if you see in this particular graph, for the output to saturate, the amount of input that you can provide is this small, right? So the input range is very small of your op-amp. But you know that all the signals that you receive, so let's say the signals that you obtain from any like sensors and all, those signals are in few micro to milliamperes, right? Or few micro to millivolts. And that range of signal needs to be amplified. So if that range of signal I want to amplify, so I need to make sure that that input range comes in this linear region of amplification, so that corresponding to the input, I can get A times output. Okay. So my idea of amplification is I should get V out as A times of V difference, right? But if I go beyond this range, if I go beyond this range, what happens is my output saturates to plus minus VDD. So in this case, what basically happens is I lose my information. If my input signal changes rather than only amplification, so basically the idea of amplification is your amplitude must change. The only difference that we want is the change in amplitude. We want to increase the amplitude of our signal in amplification. But rather than being amplified, if anything else happens to the system or anything else happens to my signal, we call it that our signal is distorted. And saturation is one of those distortions. And the moment you encounter distortions in your output signal, that basically means your information has been um, like your information is lost or your information is damaged, which you don't want. So that's why what you want is your input signal range should be in this linear range of amplification. So in order to obtain this linear amplification behavior, what we try to do is yeah. What we try to do is we somehow try to increase this linear range, okay? We somehow try to increase this linear range. Further, it will again saturate because that is how the op-amp is designed. So definitely it will saturate at plus minus VDD. But now if you look at this, we have increased this input span, right? So this increase in input span is required for a linear amplification of our signal. So in this complete region of linear amplification, we will get V out as A times of V difference. Okay. So the question arises, how do we get this, uh, how do we increase the linear range of our amplifier, right? So the idea is to increase the linear range of our um, amplifier. What we do is we introduce feedback to our system. So this is where the feedbacks comes into picture. So to increase the input range of your op-amp, we introduce a negative feedback. Negative feedback in our op-amp. So this basically what it does is it reduces the gain. So the moment you introduce a negative feedback, it reduces the gain. Maybe I can write gain only. Gain, we call it by AV or AI. This gain actually reduces. Now, since the reduction of gain, and we know that V out max can be plus minus VDD, right? And we also know that V out is A times V difference. So now, if I reduce my A somehow, I can increase my V difference, right? To obtain a constant V out. So that is the idea behind this negative feedback. Okay? So now we have understood, okay, why do we need negative feedback, correct? Then, okay. So how do we introduce these feedbacks? So feedback, basically what is feedback? Feedback is we feed output to input. So say in our op-amp, if this is my op-amp, and if I connect my output to input, then this is feedback path. Okay. If I connect my output, so in op-amp, we have two types of input. One we call as inverting input, another we call it as non-inverting input. So the idea is if you introduce input to an inverting, so this is negative one is inverting terminal, and this is non-inverting terminal. Positive one is non-inverting terminal. So the idea is if you introduce a input to the inverting terminal, in output you would see a phase difference of 180 degrees. Or from mathematical terms, your output will have a negative value with gain times of input. That is what is inverting. Inverting basically from physical significance, inverting means an 180-degree phase shift in the signal. And from mathematical point of view, you will find a negative negation in your output. So whatever you are giving your signal in input, your output will have a negative value. That is inverting behavior. In non-inverting behavior, the moment you give an input to the non-inverting terminal, your output will be positive, or your output will be in the same phase as that of input. Okay, so that is what is meant by non-inverting terminal. And also from the names itself, you can understand, right? Inverting means something that flips. So 180 degree is a flip, right? And non-inverting means nothing happens. So 0 degree phase shift. And now feedback, whether it is a positive feedback or negative feedback, also depends on which terminal you are connecting to your output. Okay. So here, this particular path is negative feedback path where I have connected my output to inverting input. Now, if the same output I would have connected to my positive terminal or non-inverting path, this would have become positive feedback path. Okay. So we have understood that for amplification, we need to reduce the gain in order to increase our input span, right? So the feedback that we would be using is negative feedback. Uh, so be mindful that positive negative can be interchanged. Okay, so what I mean by that is I can write it like this also. So never confuse it with okay, lower terminal is always negative, upper terminal is always positive. It's never like that. Always look for these signs, right? So here I have changed my input, or I should say, I have changed my feedback or negative terminal. So my above terminal is negative and lower terminal is positive. V out, V in, and this is ground. So in this configuration, okay. So in this configuration, we can see there is a negative feedback. And here I am giving input to my inverting terminal. Okay, so this is an inverting. This is an inverting amplifier. Now, if I talk about what will be the gain of this amplifier, so the gain, that is V out by V in, is minus RF upon R1. Okay. So this is the gain that you would obtain for this particular circuit. Okay. In the similar fashion, here again, what you can see is we are continuing with the negative feedback, right? Here the feedback remains same. The feedback is again negative feedback. But where I'm giving input to my non-inverting terminal. So this amplifier is my non-inverting amplifier. Okay. So this is my non-inverting amplifier, and the gain for this non-inverting amplifier is 1 plus RF upon R1. See now here, if you can observe, in inverting amplifier, the gain has a negative value. Whereas in non-inverting amplifier, the gain is positive in nature, right? If we talk from physical significance, in inverting amplifier, you will see a 180-degree phase shift. And in non-inverting amplifier, you would not see any phase shift. So the phase shift is 0. Okay, so this is basic on like op amps. Now, maybe we can start with the problems, and in each problem, as we come across the concepts, I can explain to you there parallelly. Okay. So starting with
Excuse me, ma'am.
yes.
Sorry for interrupting, ma'am. I
No,
have
no,
a
it's
doubt.
okay. You can feel free to interrupt anytime you feel like. Don't wait for the end of the session, okay? Yeah, please go ahead. What was your
Okay.
question?
Ma'am, why would we use only resistor while giving input to negative terminal, but we won't use resistor by giving input to positive terminal? Why so, ma'am?
I mean, you can use input while giving so you can use a resistor here. So let's say if I use a resistor here, I can do it like this also. Let's say this is some R and I have given V in dash. Okay. So in this way also
Won't it
it is.
change the output, ma'am?
No, it will not change because the
Okay.
idea is in your op-amp. Okay, there are few things that you need to remember, everyone. Please pay attention. In your op-amp, when you look at the input terminals, and if you try to inject current through your input terminals, the current will always be zero. Like current cannot go through your input. So you have to keep this in mind. So here I is zero. Okay. Similarly, in this region, if you are trying to inject current into your op amp, you can never do that. So here also the I is zero, right? But here I is not equal to zero. So output current of an op amp is never zero. But input currents are zero. So you have to keep this in mind that input current to an op amp is zero, whereas output current to an op amp is non-zero. This is something we have to keep in mind. It comes from how the op-amp has been designed, because what you see here is a triangular black box, right? But internally it has circuits, and these circuits are made up of devices like MOSFETs, and those MOSFETs are connected in such a way that it gives us this configuration. So you have to keep this in mind. Now coming back to your question, if I have this resistor R, okay? So in this resistor R, when there is no current flowing through the resistor R over here, so there is no drop across R, right? So V in dash and V in are same, right? And in an op amp, your potential of these two, so the if we say it is an ideal op amp, and basically the op amp has very high gain, so that means the idea is that, okay, so when we say it's an ideal op amp, so the idea is the gain, open loop gain is very, very high, almost tending to infinity. Okay. So these terminals, which are internal terminals that I'm talking about, right? The internal terminals before connecting it to anything. So these two terminals, V plus and V minus, if my gain tends to infinity, you know that V out is constant, right? So V out is AV times VD, that is V plus minus V minus, right? So if this tends to infinity, then VD should tend to zero, correct? To balance it out, if one tends to infinity, other has to come down to zero, right? To get that balance, right? So because of this, what we say, if we consider ki our op amp is an ideal op amp, then what we consider is V plus is almost equal to V minus. Okay, and this is what we call as virtual ground concept, or I should say virtual short, right? So they are not practically short. Like these two uh, points are not connected through a wire to each other. But due to this particular situation, these voltages are pulled together. So they are almost constant. So whenever we try to solve any op-amp based question, we consider our op-amp to be ideal unless anything else has been mentioned. Okay, we consider our op-amp to be ideal, and we say that, okay, so here if I say this is my VA and this is my VB, right? So I'll always consider my VA to be equal to VB. And by using this consideration only, I'll solve all my op-amp based circuit problems. Is this clear?
Yes, ma'am.
Okay. So,
Thank
uh,
you.
yeah, so that was the idea. So, one thing is that we use this virtual short concept where we consider that input terminal voltages of op-amp are always equal in the ideal case. And be it an ideal or practical or any op-amp, the input current to your op-amp will always be zero. There won't be any current going inside your op-amp, but your output current is never zero. You will get some output current. So while solving the problems, we have to keep these in mind. Is this clear? Any other doubts? Please feel free. You can unmute yourself and ask. You can interrupt me at any point of time. Yeah, please don't. You don't have to raise your hands. Please unmute yourself and you can ask. Hello.
Voltage is zero. Then
Sorry, I cannot hear you. Can you speak a little louder?
voltage is zero. One
A little louder.
voltage in charge is zero.
Voltage short is zero. I could not get your point. Where is voltage short zero?
Virtual short.
Hello?
Yes, virtual short.
Virtual short concept basically means voltages will be equal. But I never said that voltages will be zero. It will depend on what is the voltage at one point to another. Now here, if you look at this circuit where I have denoted VA and VB, in this particular situation, my VA is a floating voltage, right? I don't know the fixed value of that node, correct? But VB, I know that it is zero. So I can directly assign my VA as zero. Now, let's say in case of ground, if this was my V in 1, for example, right? So here again, if I see my VA is a floating node. Floating nodes are those nodes whose voltages are not fixed. They can change. But when a node has a fixed voltage, like it is connected to say a supply or a ground node, its voltage is already fixed, right? So it can define the other node's voltage, right? So in this case, the moment I connect my VB to V in 1, I can say my VA will see a voltage V in 1 due to virtual short concept. Is this clear?
That is one more voltage is connected externally.
Where you want to connect one more voltage?
After shorting.
After shorting, where? At which
No,
node?
you are getting what?
Sorry?
Where you are getting V plus V minus.
There is a lot of noise and I cannot hear what you are trying to say. Hello?
From where you are getting the V plus V minus voltage?
Huh.
Without voltage source.
Right. So you are saying in place of VA, if directly a voltage source was connected, then what would happen? That is your question?
Input is not there. Input voltage source not there.
Okay, so you are saying that this Vin is not there. Let's say this Vin is not there. You have grounded this, and here you have Vin. This is what you are trying to say?
Yes, yes.
Okay, so if this point is directly Vin and say the other point is also grounded, then sorry, then you know this point's no voltage, right? It is Vin. So you can continue with Vin rather than taking ground. But this never happens because if both the nodes, say if I say here I have Vn and Vb is grounded, that means both the nodes are fixed voltages, right? And at that point, implementing virtual short concept will not be valid. When you can implement virtual short concept, when you know that one node is a floating node, and being a floating nodes give me a flexibility that it can see any value from ground to VDD, right? But if a node is already fixed to a voltage, I cannot change its value. Then I have to continue with whatever value it already has. That flexibility of virtual short concept, why I'm able to apply that virtual short concept, comes from the flexibility that one of the nodes is actually a floating node. That floating node is very important for me to implement virtual short concept, because if one node is in, like in this
Okay, thank
particular
you.
case, here Vin already there, and ground node you have like Vb is grounded, and both are fixed voltages. So now which voltage would you change? You cannot change anyone, right? So here it will be very difficult to apply virtual short concept. So virtual short concept generally you apply when you have one, because all the circuits will be made in that way only, where you will find one floating node and one node where you have a defined voltage, where you can see the definite voltage over there. And at that point you can apply this virtual short concept, and you can identify the, like, you can simply assign the voltage to that floating node and continue your problem, like problem solving. So it's basically an it's a tool given to you to analyze the circuit easily. That is the idea of this virtual short concept. Is this clear?
Yeah, thank you. Thank you.
Okay. So yeah, maybe this is PM. All right. So any other doubts? Any other questions? Any other queries? Okay. So let's move on to our first problem. In this first problem, it is given that an ideal op-amp has which of the following characteristics? So what I discussed about an ideal op-amp? Yes, what I just discussed about an ideal op-amp? What were the behaviors of an ideal op-amp?
Gain is infinity.
Gain is, okay. Yeah, we can say that gain tends to infinity. What else? If gain tends to infinity, what will happen? We discussed, right? Currents will, first of all, that we can apply virtual short concept. V minus and V plus will be equal. And we also discussed about currents, right? There won't be an input current. There won't be an input current in an op amp. And this output current is never zero. These are the things which we have discussed, right? Now, based on these behaviors, can we talk about the resistance behaviors now? So let's say your output is zero. Sorry, your input current is zero, right? So what about input resistance? Rin equal to
Infinity.
by In, right? Now if In tends to 0, what happens to Rin?
Infinity.
Rin will tend to infinity, correct? Second, we already know that gain tends to infinity, right? And practically speaking, I want my I out should not be, I out is never 0. So can R out be infinity? Is it possible?
No, ma'am. Zero.
It can never be possible, right? So in ideal case, what we consider is R out equal to 0. Okay? So these are the three things that you'll observe in an ideal op amp. Is this clear? Are these resistance conditions clear to everyone? Any doubts in this?
No, ma'am.
No, right? Okay. So your first question is done and the option is A, that is Ri is infinity, A is infinity and R naught is 0. Okay?
Why I not 0?
Sorry, somebody is speaking, somebody is saying something.
I out not 0.
Yeah, I out can never be 0. You will find I out. So your op amp always have an output current. It is input current only that you know that it will be 0. So please keep this in mind because most of the times people get a little confused and they also put I out to 0 while solving the problems. That is completely wrong. You cannot put I out to 0. I out can never be 0. There might be a condition in which your circuit is biased in a way that it might give your output current to be 0, but it is not a mandatory condition. Getting my point? So I out is, you don't know about I out. It can be 0, it cannot be 0. But input currents are always 0. Okay? Okay. Let's move on to next problem. In this question, we are asked that the first dominant pole encountered in the frequency response of an compensated op amp is approximately at 10 kilohertz, 1 megahertz, 100 megahertz, 5 hertz. So the question arises, what is pole, first of all? What is frequency response, first of all? We understood op amp, right? Till now, we have seen op amp and a little bit about feedback, right? So the next question arises, what is frequency response? And from there, we'll go to poles and zeros. And from there, the term dominant comes into picture, right? So do you people have any idea about frequency response? Or I should say transfer function? Any idea about these?
No, ma'am. Can you please explain it?
Okay. So I'm not talking about just op amp circuit, be it any circuit in a system or a circuit. When we say transfer function, what we basically mean is V out by V in function. These are in terms of frequencies. So in a given system, when there is a system, you will have resistor, capacitor. Let's say inductor is not part of our electronic circuits for now. So most of the circuits, you can bifurcate them in capacitive and resistive circuits, okay, RC networks. So you know that resistor is not a function of frequency, right? It's not a function of frequency. It's frequency independent component. But when we talk about capacitor, it is a function of frequency. It depends on frequency. Or I should say its impedance depends on frequency. That is, Xc is 1 upon omega c, that is 1 upon 2 pi f into c, right? So we know that capacitor behaves differently in different frequencies. In one frequency, like at one frequency, it might behave as a short circuit wire, whereas in another frequency, it might behave as a mega ohms resistor, right? That much of impedance it can give. And it solely, so the capacitive value is same. The capacitance is same for the capacitor. What changes is the frequency, and along with the frequency, it's reactance, that is Xc, that changes. So that's why for a given circuit, it is very important to understand its frequency response. Frequency response basically means how the circuit will perform depending on the frequencies, right? So if I talk from practical perspective, what a frequency response means. So frequency response is, it's a curve of gain versus frequency, where frequency is your independent parameter and gain is your dependent parameter. Okay. So in frequency response, this is frequency response. So in this frequency response, what you try to see is, as you are increasing your frequency, how your gain of the system is changing. And depending on that behavior of gain, you would try to decide like in which range of frequency you want to use your circuit, or your circuit will be used for what functionality. It depends on that frequency range. So that is the idea of frequency response. Okay. And when I say gain, gain is again nothing but transfer function, right? Gain and transfer function are same thing. It's just gain is a number, which is basically the magnitude of the transfer function. And transfer function is nothing but V out upon V in. These both are function of frequencies. Okay. So these both are function of frequencies. Now, these transfer functions always come in a fractional form, or you can convert it into a fractional form. So it will have some numerator and some denominator, right? And which will be a function of frequencies. So now when you solve your numerator to 0, or when you solve your numerator and you find the solution to your numerator, how you find the solution to your numerator? You put your numerator to 0, right? Then you'll find it roots. These roots are basically, what will be the value of these roots? What is the variable over here? If V out is the function of frequency, what is the variable over here?
Frequency.
Frequency, right? If V out is a function of frequency, that means frequency is the variable. So if you solve the equation, the results or the solutions that you will get are the values for frequency, right? So these roots will give you frequencies. So frequency, let's say frequency 1, then frequency 2, frequency 3, so on, right? So numerator, when you put your numerator to 0, you will get roots. These values will be frequency values only. And these roots is what we call as zeros of the system. Okay? These are the zeros of the system. Or you can understand it as the frequencies which make your transfer function 0 are known as zeros. Simple? Is this clear?
Yes, ma'am.
Now, in the similar fashion, when you put your denominator to 0, okay, when you put your denominator phrase or expression to 0, the roots that you will find are again frequencies, right? Because this is also a function of frequency, right? So these roots, now we call them as poles of the system. Or in other words, the frequencies which make your transfer function infinity or your gain to infinity, those frequencies are poles of your system. Is this clear?
My frequency is variable.
Sorry?
My frequency is variable.
So that is the idea. So the idea is when you are writing the transfer function, the only variable that you consider is frequency variable. You consider that
Voltage.
resistor and capacitor. So the
Voltage is
idea is
also
in a circuit, when you have a circuit, you know the R values, C values, right? What you don't know is F value. And you know that capacitor behavior will change as F changes. So F cannot be a fixed value, right? F is a variable. And what you are trying to understand is, okay, what is the behavior of this my whole circuit when I change my frequencies from say very low frequency to very high frequencies? So that is the idea of frequency response. Is this clear?
Yes, ma'am. Ma'am, you told poles as a frequency which make gain as
Excuse me,
infinity,
ma'am.
right, ma'am?
I have a question.
Sorry,
Yes,
it's
ma'am. I have a question,
overlapping.
ma'am.
So one person is asking, you can just wait, then you can come
Hello.
next. Yeah, so the first person who was saying something, poles what?
Yes, ma'am. You told that the poles are the frequency which make a gain as infinity, right, ma'am?
Yeah, again as infinity, or you can say the transfer function goes to infinity. Those are the points we call as poles. Because you can see,
Ma'am,
right? In the transfer function, if you put your denominator to 0, the value of transfer function will go to infinity, right?
yes, ma'am. Ma'am,
And
see,
that
in
is what the,
similar terms,
yeah.
in similar terms, we can define zero as a which quantity is going zero or infinity, ma'am, in terms of zero.
When your transfer function goes to 0, because if numerator
Uh,
goes to 0, everything will go to 0, right? So that's why the roots
yes,
are
ma'am.
called 0.
We are making denominator zero and we are calling the term, we are using the term gain goes to infinity, right, ma'am? In the similar way, can we define zeros using any other quantity which is going to
You
zero
can
or
say gain
infinity, right,
goes
ma'am?
to 0. The frequency is at which your gain goes to 0. Because transfer function at the end is like when you take magnitude of the transfer function, you will get the gain, right? If
Yes,
transfer
ma'am.
function is going to 0, then magnitude of 0 will also go to 0,
Product,
right?
my product.
Uh,
So, yeah,
okay, thank you.
yes. Okay. There was another question, right?
Yes, ma'am. Am I audible, ma'am?
Yeah, yeah.
Okay, ma'am. Gain is output voltage by input voltage, right, ma'am?
Yes, yes.
Okay. Op-amp input gain is V out, V in by I in, right?
Sorry? Can you repeat once again?
Op-amp
Op-amp?
op-amp input gain is how much,
Okay, so there is nothing called input gain. When you
ma'am?
talk about gain, listen. When you
How it
talk
has been
about
the
gain, it is always output and input
op-amp
relation.
input gain, ma'am.
इनपुट
Input
गेन
gain
कुछ भी
formula.
नहीं होता है. इनपुट लिसन,
Input
इनपुट
gain formula.
गेन नहीं होता है. इनपुट गेन नहीं होता है.
Okay.
इनपुट रेजिस्टेंस होता है. Input resistance, impedance, you can call whatever you want. It will be a ratio between say input current versus input voltage, or input voltage versus input current. All this is possible, but input gain जैसा कोई चीज नहीं होता है, because gain is always a transfer parameter, or we can say it's a relation between two different um, two different ports, or in your case it is always a relation between output and input. So gain कभी भी सिर्फ input का gain नहीं हो सकता है, gain हमेशा input और output के बीच का होगा. Gain is like कि आपने कुछ दिया और आपको बाहर कितना मिला, उसका जब आप रेशियो निकालते हैं कि आपको रिजल्टेंट कितना बढ़ के मिला या घट के मिला, जो आपने इनपुट में दिया था और जो आपको आउटपुट में मिला, उसका रेशियो हमेशा गेन होता है, राइट? सो गेन कैन नॉट बी एन इनपुट गेन और आउटपुट गेन. गेन इज ऑलवेज बिटवीन इनपुट एंड आउटपुट. Am I clear? So in input you can have conductance, you can have resistance, but input gain नहीं हो सकता है. Similarly, output you can find output resistance, output conductance, all these things, but you cannot find output gain, क्योंकि output gain जैसा कोई चीज ही नहीं होता है. Gain is always output upon input. Is this clear? Am I clear? Hello? Hello?
Yes, ma'am.
Am I clear?
Yes, ma'am.
Okay. So what else? What other questions? What other questions you have? Feel free to ask. See, nobody is here to judge. You can ask. If you feel like it's a silly question, still you ask. There might be many people who might not know it. So feel free to ask. Whatever comes to your mind, feel free to ask, because this is the only time where you can interact. Yeah. Any doubt, any query comes to your mind, feel free to ask. Just unmute yourself and ask.
Ma'am, can zeros be defined as the range of frequency where the op amp will not be operable?
See, you cannot say it so simply, because it's not that easy. As your op-amp, at the end of the day, when you find the transfer function, you'll have multiple poles and multiple zeros, right? And what you get is a combination effect of poles and zeros. So things change over there. So that's why it's not that tricky. But just for the sake of explaining, I explain to keep this in mind, that it's easy to understand, right? Like zeros, so you would never confuse between poles and zeros. That was the only motive when I said zeros are the frequencies where your transfer function goes to zero. Because practically you can see, when the numerator goes to zero, the whole system will go to zero, right? And that's what the roots we are calling as zeros. It's
Yes.
just for nomenclature purpose,
I'll talk to her later.
but it's not as straightforward as you understand, because in coming lectures we'll go through Bode plots and all. There you will clearly understand how to plot these frequency responses and how the behavior of poles and zeros depend and everything. So just be a little patient. We'll come across it maybe next week or in coming week. So yeah, it will be even more clear. We'll do tons of examples and it will be completely clear to you. But for now, for the time's sake, just understand the poles are the ones where your denominator goes to zero and numerator goes to zero. We call those roots as zeros. Okay?
Okay, ma'am. Thank you.
Yeah. Any other doubts? Any other doubts?
Ma'am,
Yes?
hello.
Yes.
Ma'am, as we say, the zero is the frequency which may at which the gain will become zero.
Huh.
Do that implies that we won't get output or output is zero in that case?
I mean, that's what I said, right? It's in your transfer function. Let's say your transfer function, for example, is s plus 1k, 1 kilohertz. Okay. For example, your transfer function is this, right? So now, in this transfer function equal to 0, so that means s equal to minus 1 kilohertz, or I can say, let's make it further simple. So minus here another. So if here it is minus, then here it is plus. And this, it's s is nothing but omega. So that is 2 pi f is 1 kilohertz. So f is 1 kilohertz by 2 pi, right? So the moment I put this value over here, my transfer function will become 0, right? So the gain of the system will also become 0, right? At this, it's just key, you have to find the magnitude of this. It's a
Okay, ma'am.
slightly different scenario because it's j omega. S is nothing but j omega. So S is equal to j omega, which is a complex number. So since it is a complex number, you have to find the magnitude of complex number the way we used to do. So the gain 0 over there is slightly different than transfer function going to 0. But more or less, you can get the sense of it, right? The idea is that, okay,
Okay, thank you, ma'am.
yeah, because here s is not a real number, it is a complex number. So complex number, you have to find the magnitude of it. How do you find the magnitude of a complex number? So if I have to find the magnitude, it is root under omega square minus 1 square, right? A square, a minus b into a plus b root over. So omega square minus, so it's yeah, so it will be coming,
Zero square.
sorry,
Omega square plus zero square, right, ma'am?
here it is 1 kilohertz, right? So that's why I wrote it as 1 square.
Okay, ma'am.
Yeah, so this is your gain. So when this gain goes to 0, it will depend on this expression, right? So this is the slight difference between your transfer function and gain. But
अच्छा
more
जाओ.
or less, you get the idea, right? What is 0? So it's the transfer function when it goes to 0 is 0. And when your transfer function goes to infinity, that particular frequency, we call it as pole. Okay?
Yes, ma'am. Thank you.
Yeah. So now, yeah, coming back to the question. So till now we understood, okay, what is pole, what is 0, transfer function, everything. So what was the question? The question was that okay, so this was the question. The first dominant pole encountered in the frequency response of your op-amp would be where? So when we have a frequency response, right, we most of the times what we are concerned about in our frequency response is poles. Poles are very critical to us. Zeros, we don't zeros are not that critical for us, but poles are very important. So that's why identifying the poles and placing the poles, the pole location is very important, and we sometimes have to uh, we sometimes have to handle these poles also in order to get the behavior that we want out of the circuit. So poles are very critical for us. So let's say your your denominator, so you had a transfer function, it has some numerator, but as I said, the zeros are not of very much importance to us right now. So let's say we only consider a denominator, okay? This denominator gives us three frequencies: frequency 1, frequency 2, frequency 3, okay? So when you have multiple frequencies, definitely one frequency will be smaller than another, right? So let's say we have frequency 1 less than frequency 2 less than frequency 3. So when we place these frequencies in the frequency response, frequency 1 will come here, right? Frequency 2 will come here and frequency 3 will come here. We denote it by a cross in the pole 0 or frequency response plot. So here, the first frequency or the smallest frequency that we get in our system, we call it as a dominant pole. Okay? So the smallest frequency is the dominant pole. So why do we call this a dominant pole is, we will understand it later when we properly analyze a frequency response curve. But the basic idea is these dominant poles play a huge role in the definition of your circuit behavior. So these are very important to analyze, and their values plays a key role. That's why these are called dominant pole, right? From the term itself, you can understand that dominant means something is important, something has significance. That's why it is dominant, right? And the smallest value of the pole that you get in your system is your dominant pole. Is this clear to everyone?
Yes, ma'am.
Okay.
Yes, ma'am.
Now, when I say pole, so how do we define pole or how do we calculate pole is basically, as I told you, the circuit is made up of R's and C's, right? So the value of pole we define as 1 upon RC because it is again, it's a frequency, right? So you can write it as 1 upon 2 pi RC or 1 upon RC, depending on what is the unit you are using, whether it is frequency or radians, right? So 1 upon RC. So at any particular node in your circuit, if you want to find the pole at that particular node, you can simply calculate the effective resistance at that particular node and effective capacitance at that particular node. And you can simply write 1 upon RC on 1 upon 2 pi RC, you will get the value of that frequency. And that particular frequency is basically your pole frequency. Clear? Now,
Ma'am, can you
the
repeat that
idea
again, ma'am?
is, so when you are given a circuit, okay, you want to find the different poles. I'll let you know how to identify the number of poles in your systems, what are the poles in the system, how to calculate those poles and everything. But to be in very brief, if I say I want to calculate the pole value, what I do is at a particular node, at a particular position where I want to find the pole value at that particular position, I calculate the effective resistance at that particular position and effective capacitance at that particular position. Okay, so I can write pole as R effective, C effective. 1 upon R effective, 1 upon C effective will give me the pole value. You will get a frequency value that corresponds to the pole. Okay, so it depends on the R and C value at that particular node. Is this clear? So
Yes, ma'am.
now till now, so this is the basics of poles and zeros, right? But the idea is, in case of your op-amp, in your op-amp, you will have poles in input and output, right? Why? Because you will find an effective RC in the input as well as an effective RC in the output. So corresponding to which you will have poles also, right? So now, if I say dominant pole, means pole value is very, very small. Pole, pole frequency is very, very small, right? And when I said that pole is 1 upon RC, and if I want my frequency pole value to be very small, that means my R should be very large or my C should be very large, correct? To get a smaller pole, my R should be very large or my C should be very large, correct? Any doubts in
Yes.
this?
No,
No
ma'am.
doubts, right? So now, considering that capacitance is almost comparable in input and output side of our op amp, talking about resistance, because we know that resistance is, there is a huge difference in input and output resistance, right? In ideal case, what we considered, our input resistance is almost infinity and output resistance is almost zero. So in practical case also, the ratio would be far apart, right? So based on that, which pole will become dominant? The input pole will become dominant, right? In the op amp.
Yes, ma'am.
So your input pole is always dominant. And what is the smallest value that you can see over here, which is closer to zero? That will become your like first dominant pole. So that's why 5 hertz will be your dominant pole. Is this clear?
Yes, ma'am.
Okay, so maybe you can look into this and give me 5 minutes. I'll be back. Just analyze it once again and we'll look into it again. Okay. So is this clear? What is dominant pole? How to identify dominant pole? Why input pole is dominant pole? Is this clear to everyone?
Yes, ma'am.
Okay. All right. So let's move on to next problem. Okay. All right. So in this system, in this particular amplifier, you have to find the value of V naught. Okay. So what we will do, we will change this capacitor into the equivalent reactance. So C would become, and upon instead of C, what we use is XC, that is 1 upon J omega C. This is what we will be using. All right. So then I can simply draw it as a impedance block with both of them. All the C's are equal. So there is no change in that. And here again we will have an XC. This is V naught, right? And here you have 0. So how to find V naught? We can simply apply KCL and we can find the V naught. And this is how you also find the transfer functions also. So to find the transfer function of a circuit, what you'll apply is basic rules like KCL, KVL, and superposition theorem. These are the only rules that you would apply to find the transfer function. So this would be a good example to understand how to do that. So see, here it was grounded. So by using virtual short concept, I've put this voltage to 0, right? Now, let me do one thing. I'll apply KCL at the 0 node itself. Okay, so how do I write KCL? 0 minus V naught by XC plus 0 minus V1 sine omega t by XC plus 0 minus V2 sine omega t by XC equal to 0, right? So this is V naught upon XC equal to minus V1 plus V2 sine omega t by XC. These XC cancelled. So your V naught is minus V1 plus V2 sine omega t. Is this clear? Is this clear? So in similar fashion, you could solve all the transfer functions. Just you have to use the universal laws, that is KCL, KVL. And in some places, if you have multiple sources, like here you had multiple sources, I directly applied KCL. You could have gone through superposition also, you would get the answer. That is one
Ma'am,
source
then
at a
V
time.
naught must be minus, right, ma'am?
Sorry?
V naught must be minus, right, ma'am?
Why V naught must be minus?
Ma'am, there we write 0 minus V naught by XC.
Yeah, I have shifted it to the other side, no? When you take it to the other side, your sign changes, right? From here, I
Okay,
got
ma'am, got it.
this. Got it?
Okay.
Yeah, so this is how you got the output. And if you would have had some input, and so basically while finding the transfer function, the basic idea is you have to do separation of variable where your V out based expressions should be or term should be on one side, V in based term should be on the other side. You separate V out and V in, and then simply you would get, when you separate these two, you would get V out and V in. Simply you have to write V out by V in, and whatever the fraction that you get, that is the transfer function. But how you solve it is basically through these basic theorems only, that is KCL, KVL only.
Ma'am, hello,
Yes.
ma'am.
Yes.
Hello.
Yes.
Yes, ma'am. I have another silly question, I think, but I would like to ask.
Yeah,
Is
please.
ma'am, we have voltage gain, okay, and then we have current gain and power gain also, right?
Yes, yes.
Why we are calculating all this? Can you tell me why and how?
So why do you want to calculate the gain, right? So let's say you give
Yeah,
you
power gain, current gain, all voltage gain. Yes, ma'am.
yeah, so you have a circuit, okay? You don't know what is there inside. You have
Yes,
some
ma'am.
box. You supplied something. Let's say you give voltage to it, and you take
Mm-hmm.
output as voltage, okay? You find that you have given like 5 volts in input. In output, you only found 2 volts, right? So you know that
Yes, ma'am.
your signal or your input is lost, right? कहीं तो चला गया ना तुम्हारा 5 वोल्ट का, अगर तुम्हें 2 वोल्ट मिल रहा है मतलब तुम्हारा 3 वोल्ट तो कहीं चला गया, राइट? सो कितना परसेंट
Yes, ma'am.
लॉस हुआ या कितना परसेंट इंक्रीमेंट हुआ, to understand that we take these
Mm-hmm.
ratios, which is output on input. Those are basically gains. अब वो अगर
Okay.
if you have the ratio of voltages, then it is voltage gain. If you have ratio of currents, it is current gain. If you have the ratio of powers, it is power gain. And gain might not
Yes,
be
understood,
always
ma'am.
positive.
Got it.
It goes negative also, right? If your output is less than input, your gain will be less than 1, right?
Mhm.
So gain का मतलब हमेशा बढ़ोतरी ही नहीं होता
Yes,
है.
ma'am.
It's just the ratio of output versus input. But gain can go less than 1 also. This is basically all the time that you see what happens is gain is always less than 0. It's more like efficiency. Efficiency क्या होता है? You compare output with input, right? So in electrical terms, we call it as gain. So it basically tells you the
Yes, with
efficiency of the
multiplying with
circuit.
100.
Yeah. So in physical terms, if I take an analogy, it is basically the efficiency of your circuit. That is what we call as gain. Is this clear? Is it clear? Okay.
Yes, ma'am. Yes, ma'am.
Oh, okay. So yeah. So moving on to the next problem. Okay, so this is again another new concept in this particular problem. So it says if a differential voltage gain and common mode voltage gain of a differential amplifier is 48 dBs and 28 dBs, then what is common mode rejection ratio? For that, you need to understand what is differential gain and common mode gain, and then you can come to common mode rejection ratio, right? So till now, when I said your op amp, so you have your op amp, right? V plus, V minus, V out plus minus. This is your basic op amp. Till now, what I said, your output is equal to gain times difference of input. Correct? I always say that your output is gain times difference of input, right? So when you have different inputs, then you will get this difference, right? And the gain, what you find from this differential input, we call it AD or differential gain. When your input is different, like V plus and V minus are different from one another, the gain that you obtain, we call it as differential gain. But let's say your V plus and V minus is equal. Okay. Then the gain that you find, we call it ACM or common mode gain. It is given by V plus V minus by 2. This is what is called common mode gain. So these are two types of gain available in your op-amp. Okay. Ideally, tell me, if my V plus equal to V minus, ideally what would happen?
Virtual short.
It's short, right? V plus is equal to V minus, then I should not get any output, right? Practically speaking.
Yes, ma'am.
So basically,
Yes,
ACM is 0 in that case. Because you, in ideal case, when V plus and V minus both are equal, you should not get any output. So ideally, ACM is always 0. But practically that never happens. Practically you find some ACM, and ACM is something unwanted. You don't want ACM. It's basically an abnormality that comes into picture. Okay. So now when you say you have two types of gain and you have to find a factor that can represent your circuit's condition, right? Overall condition, which can take charge of this AD and ACM as well. So that is what we call as common mode rejection ratio, CMRR, or common mode rejection ratio. This is nothing but AD by ACM. Okay. This is nothing but AD by ACM. So it tells you how good your op-amp is, right? So from now, ideally, if you look into it, how much should my CMRR be? If ideally,
Ideally,
yes,
infinitive.
ideally it should have been infinity, but practically it should still be very high. So the idea is, if I want to design an op-amp, my op-amp should have very high AD, that is differential gain, and very low ACM, as low as possible, right? And
Ma'am, I have one doubt,
yes.
ma'am. Ma'am, when we are calculating common mode gain, ma'am,
Common mode,
when we are
okay,
calculating,
common mode gain is basically, so there is a history behind why do you need differential amplifiers. Like you could have had a single input and you could have amplified it and got output, right? Amplified output. You would analyze those circuits also where you have single input and you get amplified output. Those circuits exist. What was the purpose or need behind having a differential amplifier where you need two inputs? That is a question, right? So the idea behind using a differential amplifier or differential input based amplifier was that any signal which is common to both the terminals could be nullified, right? So what could be these signals which are common in every case or common to both the terminals? What type of signal could it be? So let's say noise can be one. So if you are in same environment, noise would affect all the scenarios in a similar fashion, which is random, but still in a similar fashion, right? So the idea behind invention of this op-amp was to eliminate noise out of signals so that you only amplify the uh, information, but you reject the noise. That was the idea behind your innovation or this invention of op-amp. Okay.
Okay, ma'am.
But what happens? Ideally, we want that there is no noise, but practically that is not possible because we still know that noise is a random thing. Even if I say that equal amount of noise is hampering my situation, there is still some noise, right? So to also, when you design the circuit, you consider everything to be symmetric and ideal so that the same signals when applied, you would get your output to be zero. That is theoretically what you have designed. But when you have a practical circuit, there are a lot of things that come into picture, right? When you fabricate a device or when you design a device, you have it in your hand. Even if everything is same, all the environment is same, still both the devices will not give you the same behavior. Because 100% matching is never possible, right? So because of that, you get this common mode issue where even if you give same signal to both the terminals, you still get the output, which should not happen. So that is where considering this ACN becomes critical, because you have to understand, okay, how much is my ACM? If it is too high, then you would go for some compensation process in order to reduce the ACM. Because ideally what we want is ACM to be zero. So that is the idea. Is this clear? The motivation behind?
Clear, ma'am.
Yeah. Okay. So, talking about this, when we are saying CMRR, which is AD by ACM. So till now we are talking in terms of volt by volt. Okay. So here it is volt by volt, and here it is volt by volt. When we convert it to dB, how you convert volt by volt to dB? So AD, if you want to calculate in dB, it is 20 log.
20 log.
Yes, AD V by V. Right? Similarly, ACM also, if you have to calculate, it would be 20 log ACM V by V. So if mathematically you have a fraction, and when you take log of it, log में क्या हो जाता है? It becomes subtraction, right? If there is a fraction mathematically, when you take log of that fraction, you would get subtraction of numerator and denominator terms.
Yes, ma'am.
Am I making sense? Yeah. So basically what I mean is log of A by B is nothing but log of A minus log of B. This is something that you people know, right? This is basic logs property.
Yes, ma'am.
So in this way, my CMRR would become AD in dBs minus ACM in dBs, right? So based on this, what will be my CMRR? If it is 48 for AD, this is AD, 2 for ACM. So what is my CMRR?
46.
Yes,
46.
46 dBs. Any doubts? Is this clear?
Yes, ma'am.
I know it's a lot of information. Each question is a new concept, but be a little patient, listen to it carefully, and you can go back, reiterate through the notes, and also go through the lecture video so that you can become confident in these concepts. Okay. Also, it's not something which is like you can take them lightly, because all these concepts are very important. Like in future analysis, all these concepts are very, very important. So each problem, each concept that I'm paying so much attention to are very important. So yeah, please be a little patient. You try to understand as much as you can, but please go through it again, okay, after the class. Right. So this is another concept where now in this particular problem, you have an op-amp with a given configuration, and it has an open loop gain of 100. It has an open loop gain of 100, and you have to find the closed loop gain of V out by Vs. So when we said an ideal op-amp, so what we basically meant is the open loop gain of that op-amp is infinity. That was the idea. But now here you have your open loop gain as 100. So if I would have considered that, let's say my op-amp is ideal, then what was my gain? V out by Vs, ideally. If this was an ideal situation, what would my gain have been? Which is minus R2 by R1, right?
Yes, ma'am.
That is minus 10. This is what you would have gotten ideally, right? But let's see what happens when you consider this practical case, okay? So here we will try to draw a small signal equivalent of this particular op-amp. So here you have Vs, let's say this is Va. So what we get here is 100 times of Va. You have the resistor R2 connected, and this is V out. Okay. So this is the circuit, right? You can see that resemblance between the two, right? So this was the circuit given in the question, and this is the equivalent circuit that I have drawn. Can you see the resemblance?
Yes, ma'am.
Yeah. So this is what we call small signal model. It's not this easy to draw small signal models. Maybe when we'll do BJTs and all, in those circuits, we can take up one example to actually draw a small signal model for a device of, say, BJT or MOS. But anyways, for this particular example, these two are somewhat equivalent, right? And now let's find what we need to find is V out by Vs. So for that, I'll again start with KCL. Let's say KCL at this node VA. This is ground. So let KCL at VA. Okay. So VA minus VS by R1 plus VA minus Vout by R2 equal to 0. Also, Vout is 100 times of VA Vout is also 100 times of VA, right? Because this is Vout and corresponding to that you also have this 100 VA. So these two equations. So substituting this over here, or we can do it other way around. Any way would work. So for now, let's do this way. So I'll make it an equation based on VA and VS. R1 plus VA minus 100 VA by R2 is 0. So that is VS by R1 equal to 99 VA by R2 minus VA by R1. So that is VS equal to VA R1 99 by R2 minus R1. So this is so VS equal to VAR1 99 R1 minus R2 by R2 R1 now in place of VA I can put V out by 100, right? So VS is V out by 100, 99 R1 by R2 minus 1. So V out by VS is 100 by 99 R1 by R2 minus 1. So that is 100 R2 upon 99 R1 minus R2. We know the values of R1 and R2, right? How much is that? R1 is 1K, R2 is 10K. Okay. R1 so if it is 1000 by 89,
And shouldn't it be 89K?
Yeah, but here also it was K, right? So both the
Okay,
K's are
okay,
1.
okay.
Hmm. Yeah, so in this way we can solve this and we'll get V out by Vs. So simply basically you have to apply KCL KVL to solve the equations all around. That is the only idea. Okay. Now moving on to the next problem. So see, in this problem, again we have an op-amp circuit with Vi is given V1 sine omega t plus phi, right? But if you observe very carefully, this Vi is connected to both inverting as well as non-inverting terminal, right? And then we have to find minimum and maximum values of phase in radians. So, in case of inverting configuration, you get V out dash as minus RF upon R1 into Vi. Correct? This is inverting configuration. In case of non-inverting configuration, you get the gain factor of 1 plus Rf upon R1, but the voltage that you should observe is this particular voltage Va. Okay? This particular Va. Now, what is Va? So, Va, if you observe, it is, so let's say इसको I write as 1 upon Sc. Okay? So 1 upon Sc upon R plus 1 upon Sc into Vi. So this is 1 upon 1 plus RCS Vi equal to Va. So this is the potential that you need to put here. And the complete V out would be V naught dash plus V naught double dash. Okay. So okay, you have to find the minimum and maximum values of phase. V naught is minus Rf upon R1 Vi plus 1 plus Rf upon R1 into 1 upon 1 plus RCS Vi. So V naught is Vi minus RF upon R1 plus 1 upon 1 plus RCS plus RF upon R1 into 1 plus RCS. So V0 is Vi minus RF 1 plus RCS plus R1
Ma'am,
plus
what is S here, ma'am?
S is J omega C. S
Okay.
is J omega. So I have converted my C into this. I've converted the capacitance into its reactance, and we can write J omega 1 by J omega C, or we can simply write SC. So S is also like it's in frequency representation. We write S, or you can write J omega. Both are fine. It's the same thing. Okay.
Okay.
RCS. Okay. Oh, now simplifying. Minus RF RCS plus R1 plus RF. These two are cancelled. Upon R1 1 plus RCS. Okay. कहीं कुछ मिस्टेक हो रहा है क्या? It's following correctly only, no? Okay. So anyways, V out is Vi R1 minus RF RCS upon R1 1 plus RCS. So considering RF equal to R1, just for simplification, why? Because the moment you put this condition, your V out by Vi becomes very simple. It becomes 1 minus RCS by 1 plus RCS, right? So this is much easier to solve. So that is the only intention of considering this equation, this particular condition. So in this condition, now if I expand it to normal form, this is 1J omega RC by 1 plus J omega RC. Now you know how we write phase, right? If you have complex numbers, how do you write the phase of those numbers? So I want to find the phase of V naught by Vn. So how do I write it? It's tan inverse. Yes. Omega RC minus tan inverse omega RC. But okay, so here it is 1 minus tan inverse would be 1 minus j omega c का phase क्या आता है 1 minus j omega, yeah, minus tan inverse, fourth quadrant, right? 1 minus j omega RC. So you can simply look into the phase chart because it depends on, right, the phases, like which quadrant your complex number will appear. Based on that, you write the phases. So just you can revise it once. And from there you will get this. So you will get minus 2 tan inverse omega RC. Okay, this is the phase of V naught by Vi. Now here, when this is the phase, so what can be the minimum and maximum values that you can get out of this phase, right? So what is the maximum your tan inverse value can go? Or I should say minimum of omega RC. What is minimum of omega RC? 0 degrees. 0, right?
Yes, ma'am.
Minimum of omega RC is 0. So tan inverse omega RC in this case would be 0 degrees, right? So 2 times tan inverse would be again 0, right? Minus 2 tan inverse omega RC would again be 0 degrees, right? So this is minimum phase, correct?
0 to 90, I think.
Yes.
Infinity.
0 to 90 आ रहा है क्या? Will it be 90?
No, 0, ma'am. It will be 0, minimum and
Max
maximum, I think.
max value of omega RC कितना हो सकता है? Tan का maximum कितना जाता है? What is the
Infinity, that is
maximum?
90.
Yes, maximum it goes to infinity when tan is 90 degrees. So in that case, if omega RC is infinity, then tan inverse omega RC would be 90 degrees, right? So minus 2 tan inverse omega RC कितना हो जाएगा? 180 degrees, right? Or I should say minus 180. So the maximum phase, minimum to maximum phase, the phase range that you get is 0 to pi by 2, minus pi. So this one. Is this clear how we solved this problem?
Yes, ma'am. Yes, ma'am.
Okay, so you can go through this once again, just in case. Yeah, so moving on to the next problem. Oh, again, this is a very different concept, a very new concept, but I feel we have done a lot of new concepts in each and every problem. So do you want to take up another new concept right now, or we can stop here and take this problem in next week? Meanwhile, if you have any doubts, we can discuss. We have 5 to 10 minutes more. Because here I need to explain you the concepts of comparator and everything. So it's a different domain altogether. So I don't want to rush it within 1-2 minutes. So what I suggest is we take this particular problem next week. But yeah, what do you people want? Do you want me to take this problem now? I can take it, but it will be a little rushed. Or else in next week we can take it with like
Next
patience,
weekend.
please.
Next week, ma'am.
Okay, so we can take this problem and consecutive other problems also in next week. Meanwhile, till now, whatever we have done, do you have any questions on that?
How did we get -2 tan inverse?
Okay, so this comes from phasors, like when you have complex numbers, how to get the phase out of complex numbers. So it comes from there. So why I got minus tan inverse omega RC when I had 1 minus j omega RC, it depends on, so if we know that, so these are 4 quadrants. So in first quadrant, sine, cos, tan, all are positive, right? Tan, cot, all are positive, correct? In second quadrant, the moment you go to second quadrant,
Only sine
sine,
and cos. Okay.
sine is positive,
Okay.
right? Cos is not positive here, right?
It's not like something related to trigonometric quadrants.
Yeah, trigonometric quadrants only.
Oh, okay. Okay, got it.
So, like it's related to trigonometric quadrants as well as relating it with complex numbers.
Okay, ma'am.
So, when you coincide trigonometric quadrants with this complex numbers, when you merge the two planes, so from there you get this, whether it will come as pi minus tan inverse theta or pi plus tan inverse theta, pi by 2 minus, pi by 2 plus, minus, plus. It all depends on that. So
Okay,
you
ma'am.
can look into, yeah. So you can simply look into any book, any mathematical book. You can just look into how to calculate phase of complex numbers.
Okay, ma'am.
Calculating the phase of complex numbers, you can find this. So it comes from there. So it's sometimes it's a little confusing also when you are not in touch. All of a sudden, if it is asked what will be the phase, because sometimes it gets a little tricky because you need to remember a few things. But more or less, it comes from there when you coincide trigonometric planes like that quadrant, those 4 quadrant behaviors along with your complex plane. That's the basic idea.
Okay, ma'am.
You'll
Thank
find it in any mathematical book, or simply when you'll search online also you can get through this. Any other doubts?
Ma'am, can you show the third solution once? Third question solution.
Third question. Yeah, this one, no? Yes.
Yes, ma'am. 1 minute.
You can use your own conventions for KCL, KVL. Just make sure you follow only one convention throughout. Don't get confused in this plus minus things, okay? You can use your own convention of positive, negative, whatever, but just don't mix 2, 3 methods together. You will get confused. Follow one throughout. Because if
Yeah.
you follow one convention throughout, you'll get the answers correctly. If you merge 2, 3, you will mess it up completely. Okay? So this is my way of writing KCL. You can use your convention. It's up to you.
Ma'am, I have a doubt, ma'am.
Yes.
Can we interchange the positive and negative inputs, ma'am, of op-amp?
Interchange
Or is
positive.
it like,
Yes.
or is it like we have to keep the negative on the top side or the positive on the bottom side, ma'am?
See, positive, negative, you can draw top and bottom. It is fine. But the if I'm saying negative feedback, I know that my output connects to negative terminal only. It can be on top side, it can be on bottom side. I can draw it on top side, bottom side, that doesn't matter. But at the end of the day, negative feedback is negative feedback. That is, output should connect to negative terminal only. You can draw it from on top side or bottom side, that doesn't matter. It's just pictorial, right?
Yes, ma'am. But I have studied now I'm studying the op-amp characteristics. No? I have seen that positive on the top side and negative on the inverting terminal as positive and non-inverting terminal as negative, ma'am.
So it's basically just representation. That's what I'm saying. You understand the physics behind, right? What does positive terminal and negative terminal mean, and how do we use them?
Yes, ma'am. Yes, ma'am.
So depending on that, you can draw it as you want. It doesn't matter. The physics should not change. When I say negative feedback, but like in the same diagram, if I switch my positive and negative, okay. So
Yeah, ma'am.
now that feedback is not negative feedback. That becomes a positive feedback. So my circuit is completely new circuit. It will not be an amplifier anymore.
Yes, ma'am.
Yeah, so its functionality is different, everything is different. So physics should not change. Pictorially, you can draw it like that. You can just bring down that feedback path to downwards. It's fine.
Excuse me,
Okay,
madam.
ma'am. Thank you.
Yes.
Excuse me, madam. Can we solve this question 3 by inverting summer concept?
Inverting summer concept.
Directly using the final result of inverting summer amplifier.
I mean, yeah, you can do that. So it's the same thing, right? I have solved it from zero. You can directly apply the equation. In this way, just the thing is, if there is some anomaly, it gets caught. Otherwise, you can use the formula as well. If you can see it directly applies, so you can apply it. That's
Okay,
fine.
thank you, madam.
Yeah. Any other doubts? Okay, so if you don't have any doubts, maybe we can break over here and meet next week at the same time. Until then, you people can go through the document as well as the video. I'll upload immediately. And that's all for today. Thank you for joining, everyone. See you all next week.
Thank you, ma'am.
Okay. Bye. Have a good evening. Sure. Okay. Bye.